any fractional exponent can be written in this radical form. Usually the most common radical forms you see is square root, which will not have any little 2 there. It's just a symbol. So this is square root. And then there's the cube root. So you'll see a little small little 3, and then this little house type, this little roof type symbol. So this is called a radical symbol. If you had x to the power 1 over 3, so this is a fractional exponent, that's the same as cube root. Okay. So that's what this is referring to. When you go, you can switch between the radical form and the exponential form, where the number in the denominator represents what the number of your radical should be, and the number in the numerator stays associated with your base number. And then radicals, if you're multiplying, you can combine the insides under the same radical roof, or you could split. And the same goes for division. However, when it comes to adding and subtracting with radicals, this is a common mistake. We have this. So square root of a plus square root of b is not equal to square root of a plus b. Okay. And the same goes for subtraction. So even though square root of a times square root of b does equal square root of a times b. So if there's multiplying, you can multiply it inside. When it comes to adding or subtracting, you can't split or combine the square roots. And here's an example. If you have square root of 9, and then you have square root of 16, well, square root of 9 is 3, square root of 16 is 4, that gives you 7. But if I had them both being added underneath the radical, so I have 9 plus 16, that gives me 25. Then I take the square root, I get 5. These are two different results, and that's because these are not equivalent statements. And generally, if you're going to add or subtract radicals, you can add or subtract the ones, if they're like radicals, that just means the inside of the radical is exactly the same. So notice here we have square root of 3, and here we also have square root of 3. So when I add, what I'm really adding is their coefficient. The coefficient is, in this case, 1, and in this case, 5. So when I add that, I get 6 square root of 3. In this case, we have cube root of 5 with both of those numbers. So we can go ahead and add or subtract these values. So 7 minus 4 would give us 3. Okay, and then just this one final example where we switch between exponential form to radical form. So again, what you can do is the number in the denominator of the exponent forms the radical portion, and then you have 27 squared. Now, sometimes this is generally the setup where you have this is equal to this. However, if you want, you could also put the square on the outside of the radical. So what I mean by that, this is equivalent to this. In some cases, it may make sense to do the radical first and the the exponent later. So if I want to solve this, square root of 27 is 3, so I have 3 squared. And that's the advantage of writing it in this format versus the other one. In certain problems, it may actually be simpler to solve this. Okay, well, 3 squared is 9. So here again, this one, we have a 2 in the denominator, so that's square root of 9 cubed. But I can also think of this as square root of 9 and then cube on the outside. So square root of 9 is 3. So I have 3 cubed, that gives me 27. Okay, here we have a negative attached to our radical. So how does this, attached to the fractional exponent? So what you have to do is to apply the radical, you need to first make this exponent positive. So we actually need to rewrite this statement as 81 to the power of 3 over 4. And now we can change it to radical form. So you can never change an exponent to radical form if it's negative. You need to convert it to a positive exponent. All right. So now this is 4 root of 81 cubed. Or again, you can do the 4 root part first and then take the cube. Okay. So this is the one that I don't know on the top of my head. Okay, so 4 root of 81 is 3. So we get 3 cubed, and that gets you 1 over 27.